right, so last time we have developed our definition, last couple of times, definition of the derivative at a specified point. So that is this one right here. So this is our limit as x approaches c of f of x minus f of c over x minus c. Actually, right here. Here's kind of the three different ways we might talk about it in terms of the vocabulary. But that's our first definition of the derivative, and it's the derivative defined at a specified point. So notice that, at a specified point. Now what we're going to talk about is a limit definition of the derivative, but as a function. So I guess I actually had this right here. So that's what we knew from 2.1. Now we're going to look at another definition of a derivative, but this one is going to be the definition of the derivative of the functions. When we're done, we're going to have a function of x. So we're going to start off, it's the same old logic we were applying before, okay? Meaning we are looking at using the idea of the slopes of these secant lines and letting them approach the slope of the tangent line. So the first thing I want us to think about is, well, what's the slope of the secant line? But we're going to denote this a little differently. So this time we're going to start with kind of the first point, the point of tangency interest is what I'm calling x. So this is going to be not for just one specific c, but we're doing it in general for any x. So that's why we start with just x and not a particular c. So we say, okay, x is my point of tangency interest here. So what I'm doing then is I'm going out a distance of h units away. So on the x-axis here, I go from x, and then I go down to the right here, h units away, and that gives me another point, which could be then expressed as x plus h. So on the function, I have this point now is the ordered pair x plus h. All right, so this is now the point on this function. It is x plus h, and then its output, of course, would be f of x plus h. So that is this point on the function right here. And then, of course, we have our first point on the function, and that was this little guy right here. And so this was just any x f of x. And so our slope of our secant line, just like before, is just simply change in y over change in x. Okay, so let's write that up here. The slope of our secant line is still going to be change in y over change in x. So this time it's going to look like f of x plus h minus f of x, there's my change in y, and then divided by my change in x, which is going to be x plus h, that's the first x coordinate, if you will, x sub 2, and then minus x. Well, of course, then what happens with this is the x minus x becomes 0, and so what we now have is the slope of our secant line right there. So just like before, we're going to move that second point in closer. So visually what we're seeing here is now we're describing that as being a distance of h. So I'm going from here to here. So there's my h, and then I'm continuing as we look through all these pictures from here to here. There's my h. And so what we're seeing as we go through these pictures is we are letting h go to 0. So this is the limit definition of the derivative giving us a function of x when we're done. So not just for a particular c, but for any c. So where we end in this last picture here, this is the definition of our derivative. So the slope of the tangent line, is the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is the second definition of our derivative. And so our derivative is going to be denoted, again, our first notation we're learning here is just this prime, this apostrophe notation. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. All right, so the difference is when we're done here, as I've been saying several times, is we are going to have a function f prime, but it will be a function of x. And so it's like doing this in general for any point we want. And so we'll be able to sub in whatever c I want rather than just doing the definition we did last time for a particular c. All right, so let's take a look at, so here it is, just kind of rewritten, summarized, just like in a box from your book there. So let's look at an example. And so we're going to use the definition of the derivative that we just developed here, the derivative function, the definition of the derivative function to find f prime of x. So number one, suppose we have f of x is equal to 5 times the square root of 2x minus 3. So we're going to do a few different parts to this one, but we're definitely going to start off finding our f prime of x. All right, so first we need to start with the definition of the derivative that we have up above in our box. So this is, of course, our limit as h goes to 0 of, now, f of x plus h. So that says that we go in to the f of x function, and we are going to take out the x, and every place where there used to be an x, we are replacing it with the quantity x plus h. So that's the, definition essentially of how we define working with compositions that way. So that's my f of x plus h minus just the f of x, so the original function. So that's just my f of x there. And that whole thing gets divided by h. Okay, so this was right up here. There's my f of x plus h. And that is this part right here. Making sure you get that correct is pretty key. And then suppose we have minus, of course, the f of x, and so that's this portion right here, and then it's just all divided by your h. All right, so that's our definition of our derivative. Now, if we were try to evaluate this right now and let h go to 0, we would have 5 times the square root of, well, if h goes to 0, that would just be 2x minus 3, and then that's exactly what I have in the second term here. And so, of course, what am I getting? I'm getting 0 over 0. So we get an indeterminate form. So we're trying to evaluate a limit. We try direct substitution. We get an indeterminate form. All right, so what we want to think about is, well, what are the things that we do with 0 over 0? We typically perform some sort of manipulation to get it into a different form. And with radicals, that most often means multiplying by the conjugate, especially when you have a radical that involves like a binomial like that. So what I might do here, let's rewrite where we're at. Limit as h goes to 0. Keep that limit notation until the very end. You haven't been able to evaluate your limit yet. Let's go ahead and first just kind of factor out that 5 that's in both terms. Constant multiples are going to get carried along. In fact, we could bring that out in front of the entire limit if we wanted to. And there's no need to, though I think just instinctively a lot of students would probably distribute through that too. So I'll go ahead and do that under the radical there. So here's what I have. I'm just factoring out the 5 just to kind of simplify the appearance a bit. All right, so what are we going to do? We're going to multiply by the conjugate. And here I have a binomial with 2 radicals. So remember, the conjugate is going to be each of the radicals left the same, but then just multiplying the conjugate then changes the sign in between those 2 binomials. So notice I'm not changing this into like, oh, what's under the radical, that becomes 2x plus 3. No. The conjugate of root A minus root B is going to be root A plus root B. You don't change what's underneath of those square roots. And that's important here. So I am multiplying by the conjugate, and so that's what we have. All right, now if you remember when we did this, we will multiply out, and again, I'm going to just bring this 5 all the way out in front of that entire limit. Constant multiples can be carried along that way. So when we multiply out our two binomials, that's what we want to do in the numerator. You want to definitely multiply out where you were multiplying by the conjugate. So when you have root A times root A in that first term, you're just going to get A, meaning what's under the radical. So in the first term, I'm simply going to have the 2x plus 2h minus 3. Then I'm going to have plus the multiplication of the two different radicals, and then minus the product of the two different radicals. Same terms, 1 plus 1 minus, so I'm not even going to write that. And then I have minus, and then in the last term, again, root b times root b is just going to be b, meaning what's under the radical. However, because what's under the radical is a binomial, that does need to be in a set of parentheses. And then this is all over, and in your denominator, you don't want to multiply out. Multiply out where you multiply by the conjugate. So in this case, that's in the numerator, but then we're going to leave the denominator just like it is. Because remember, our goal here is ultimately going to hopefully be at some point to do some reducing. And so we reduce when we're eventually going to be in a factored form in that denominator. Okay, so what do I have going on here? So let's just kind of take a little look in my numerator. I have my 2x plus 2h minus 3. And distributing through the negative, I have negative 2x and a plus 3. So, of course, I have some terms that are becoming 0, the 2x terms and the 3. So here's where we're at. We now have 5 times our limit as h goes to 0 of, in the numerator, the only term that's left is the 2h. And in the denominator, it's more of a pain to just rewrite it than it is anything, but it's the h times the product of the binomial of those two radicals. And so now, and not a moment before, but now, because I have a product, I have 2 times h over h times that binomial, now I can reduce my h over h. And so this is, your prompt. Hopefully you're getting better with recognizing that from all of our limit work. That's our prompt that we can now look at reevaluating the limit, letting 0 go to h go to 0, sorry. So I have 2 over, and then what I have left in the denominator is 2x plus 2 times 0 in for h minus 3. And then plus square root of 2x minus 3. So it looks like I have a 10, either up in the numerator or out in front. And then I have, this is really just root 2x minus 3 plus another root 2x minus 3. Those are like terms. Root a plus root a is 2 root a. In this case, of course, that a, we have root 2x minus 3. And so my last step here, I can actually do that division. 10 divided by 2 gives me 5. And so this is my final answer. I have 5 over the square root of 2x minus 3. Okay, so this is our f prime. This is our derivative for not just a particular c, like in 2.1, but this is our derivative for any x. So any x that I want to sub in, I can find the slope of the tangent line at any point. So a lot of times I tell my students to kind of think of this as a formula that will give the slope of the tangent line at any x location on f of x, or just at any x, that's fine, just at any x. So think of this as now being your formula for the slope of the tangent line. The slope of the tangent line to the curve of f of x at any point x. So this is the benefit if you're thinking, you know, why would I need two limit definitions of the derivative? Because this one now is in general for any x, not the slope of the tangent line at a particular c value. You can sub in any c value, any x value. So in fact, let's do that here. Let's see how that would work. So now suppose we were asked to find kind of the classic question here. So let's find the equation of the tangent line. So let's find the equation of the tangent line to f of x. So it's always the equation of the tangent line to the original function. And now we'll say at some specified point. So at x equals 2. So I want to know the tangent line specifically for x equals 2. All right, so notationally, the slope of the tangent line at x equals 2. So just kind of seeing some different notations. When you use your m and then that little sub-tan, slope of the tangent line, and I've used this before, this straight line means evaluated at, and we're going to evaluate it at a particular point, and in this case it's going to be at x equals 2. Okay, so mechanically, I mean, what are we saying here? We're saying that we are evaluating, this is kind of just a different way to denote it, f prime at this specified point at 2. So these are both kind of saying to do the same thing. So we are going into our formula for the derivative, that formula that can give me the slope of the tangent line at any point. And the point that I want it for is at the point x equals 2. And so now, I was subbing in x equals 2. Now we're going to be able to get this exact slope at this point. So my slope is going to equal 5 over the square root of 4 minus 3, of course, is just the square root of 1. Root 1 is 1, and so this is 5. Okay, so this is my slope, and there's two things we need in order to find the slope. So again, that's my slope. And the other thing I need is an xy ordered pair. So I need a point on the line. Right now, I have just the x-coordinate, of course, just the x-coordinate. So now, my point that I need is x equals 2. And then whenever you need a y-coordinate, it's always subbing that back into the original. So you're doing f of 2. So whenever you need the y-coordinate, you're going to the original, not to the derivative. The derivative is how you get the slope of the tangent line. The original, just like always, is where you're going to get your y-coordinate. Now, coincidentally here, they're the same, but in general, that is not true. So there's my point. Okay, so now if I have my xy ordered pair, and I also have my point on the line, so now here's what I now can do. Of course, point slope formula, y minus your y1 equals the m quantity x minus your x1. So your y minus 5, and it's the x that's the minus 2, and the slope that we're subbing in, of course, here is the 5. And so here's my equation, right? I have a y minus 5 equals the 5x minus 10. And so just adding your 5 to both sides here, your equation of your tangent line is y equals 5x minus 5. Y equals 5x minus 5. So this would be the actual equation of the tangent line. All right, one last part to this question, and then we'll end this video. Let's now also identify the domains of both f and f prime. And then I want us to make a little observation based on that. All right, so if we remember, f of x here was just equal to, up at the top, it's the 5 square root of 2x minus 3. Now, whenever you have any even index radical, in order to find the domain, you need to take whatever is underneath of that even index radical, and it needs to stay greater than or equal to 0. So we need to take what's underneath of that square root and say this 2x minus 3, square roots can't be negative, so it must be greater than or equal to 0. So obviously adding your 3, 2x is greater than or equal to 3, and dividing by your 2 here, you get that your x is going to be greater than or equal to, I probably don't need to put that in, x is going to be greater than or equal to 3/2, or 1.5. So if you wanted to write that in interval notation, that's often nice. This would be a bracket from 1.5, 3/2, inclusive to infinity. So there was this or equal to, and that's how we know it is a square bracket. Okay, so this is our domain of f. Now let's take a look at the domain of f prime. So f prime was, so our derivative here, f prime was ended up being 5 divided by the square root of 2x minus 3. Now we have the same kind of initial issue, right? Because a square root anywhere we know means that what's underneath of that square root, just like before, is going to have to be greater than or equal to 0. I mean, that was true with f, and it certainly is going to be true with f prime. However, we have an additional issue here, and that additional issue is the fact that this whole thing, this whole radical, I should say, is in the denominator. So this entire square root of 2x minus 3 is in the denominator. And we need to know that then the other issue is that denominators cannot equal 0. And if I think about this from the perspective of it being like an entire denominator, and maybe you don't need to think so hard on this whole thing would equal 0 when 2x minus 3 would equal 0, and that of course happens at 3/2. So x can't equal 3/2. So we have two issues here. We had the square root issue just like before, but now we also actually need to throw out the 3/2 because that would actually make the denominator 0. And so what this ends up telling us is the domain of f prime is not going to include the 3/2. So it's 3/2 to infinity. So the observation that I want you to make here is, so here, an early observation is to just kind of notice something, and that is that the domains of f and f prime are not necessarily going to be the same. They are not the same here. And in fact, what we're going to lead into next time is we're going to talk a bit about what it means to be differentiable. And if I say, where is f differentiable? We're really just, initially we can think about talking about it like that's just the domain of f prime. Where a function is differentiable is saying where does the derivative exist, is saying what is the domain of f prime. That's what we're going to be looking at. And we're going to start to see that there's different things that happen graphically on a function that might cause f prime to not exist there or to not be differentiable. And so that's what we're going to kind of lead into more next time. But for right now, it's just kind of this early observation to say, hey, wait a second here. The domains of these functions, the function and its derivative, are not necessarily going to be the same. There's going to be places on f prime that won't exist. And so that's what later we're going to talk about as being not differentiable. All right, so we will come back and talk about some of those concepts next time.